So you see the screen? You are seeing the full screen?
Yes, sir.
Okay. So last time we were discussing management functions involving constraints. So we have the function is that, and we were minimize and external z. So even if 0 z equal to 0. So one of the examples, and I said that there's a way of doing it where you can perhaps substitute for x and y and these two relations p1 x y z equal to 0 and p2 x y z equal to 0. You can express z in terms of x and y and substitute in x, y, z, and then you have a function of a single variable, you can minimize it. But that is usually quite cumbersome if you cannot solve P1 x, y, z and P2 x, y, z to get z as a function of x and y. So another way, of course, was you can write down the total differentials df, dp1 and dp2, and then substitute from dz from dx and dy in dz. Then you can get df as a subfunction of dz just like here. What I'm doing it here, and then you could again apply the maximum minimum by setting this weight of these up to 0. Well, there's a better way of doing it, which is known as the method of Lagrange multiplication. If instead of minimizing the function, f to minimize p, which is given by f of x, y, z plus lambda 1 p1 x, y, z plus lambda 2 p2 x, y, z, where lambda 1 and lambda 2 are what are called are the Lagrange multipliers. Right? And so what we have now is df equal to 0 would bring df plus lambda 1 dp1 plus lambda 2 dp2 equal to 0. And we have the following equations. That is, we will have the equations which correspond to dv by let me use this as an example that's much easier. Okay, so let me consider the following. So consider two surfaces. So two surfaces basically the following is equal to x plus 5. So this is one surface. And a second surface, which is x plus 5 plus z equal to 1. So this is the second surface. So the P1 in this case would be x1 plus 5 minus z, and P2 equal to 0, and P2 is equal to x plus 5 plus z minus 1 equal to 0. So these are the two surfaces that I have. Now, let us consider the intersection of two surfaces intersection of two surfaces P1 and P2 is a curve, because you take two sheets of paper and then you kind of split one of them and then pass another one through this slit, and you will see that you have actually intersected two surfaces, and what you have is a curve. So, for example, like this is one surface, and this is another surface, okay, and the curve and this is the intersection, okay, of the two surfaces. So that's the curve, okay. So now what I want to do is, what is the shortest distance from the origin to the curve. So I have x, y, z here, and I'm looking for the point x, y, z for which, uh, uh, sorry, really. Okay, I'm looking for the point x, y, z for which the distance is this function. The distance is going to explain to z. So if R squared is minimum, R is also minimum. Okay, so I want to minimize f with respect to x, y, and z, and constraints T1 equal to 0 and T2 equal. Okay, so you see the problem. The problem is basically trying to minimize the distance from the origin to this point, which is the square root of x squared plus y squared plus z squared. I'm actually minimizing x squared plus y squared plus z squared itself, so it's easier. Subject to these two constraints. So if you want to do that, then you will have the following. Do these PC1 is equal to quantity times PC1 is fine. Okay, and x plus del P1 by times dy plus del P1 times minus del P1. This is what P1 is. P2 equal to actually example minus x because that's the one that so I would take this part to be minus 1 plus and just that I want again. So, and what is dp2? X plus y plus minus 1 equal to 0. So that is dx plus dy plus dz. Okay, so that is dp2 and df df is or 2x dx plus dy plus dz. So all the things are they are shown here. Here by dy by the other. So now if I look at df if I'm minimizing this equal to f plus lambda 1 t1 plus lambda t2, then I will have to have three differences. I will get the form that is del f by del x plus lambda 1 del f by 5 plus lambda 2 del f by del z equal to similarly del f by 5 plus lambda 1 sorry del c1 by del plus del p2 by del x. Okay, plus lambda del c1 by del 5 plus lambda 2 del p2 by del y equal to 0. What I have got is this quantity del capital X del 0, del capital F del delta to 0 and del capital F. So that is the first two. by third equation del f plus del f del phi 1 by del z plus lambda 2 del phi 2 by del z equal to 0. So now having been done with for the del phi 1 next del phi 1 by del phi 1 as well as del phi 2 by del x, del phi 2 by del y, del phi 2 by del z, and I also have evaluated 2x dx 2y dy 2. That is it. And this these things that we like I had a okay. So that will be so that will be the first equation. Only we have these three things that are still set zero multiplied by lambda 1 and lambda 2, and then the second thing. So I can write on these three equations. I have 2x minus lambda 1 9 plus lambda 2 equal to 0. Okay, that is equation 1. And equation 2y minus lambda 1 plus lambda 2 equal to 0. This is the second equation. And the third equation, 2z plus lambda 1 plus lambda 2 equal to 0. This is the third equation. So what I have is these three equations plus the fourth equation, which is p1 equal to 0, p1 x y z equal to 0. P1 x y z equal to 0 is the fourth equation, and P2 x y z equal to 0 is the fifth equation. So I have five equations and five unknowns. Okay, the five unknowns are the x y z. I have to find out the point which is closest to the origin, and then lambda 1 and lambda. So these are the five unknowns, and these are the five. Okay, so what I will do is I will use it and then the values of lambda 1 and so using I will get the lambda 1 and lambda 2 are the following. I'll get the third equation 2 from equation 1. I'll get twice. Okay, minus lambda 1 y minus x is equal to 0. This is subtracting 1 minus 2, and so I will get lambda 1 is equal to minus 2. Okay, so I have already got lambda 1. So I substitute this value, which is the following, that I have 2x minus plus 2. If I substitute lambda 1 is 1. We get 2x plus 2y plus lambda equal to 0, or lambda 2 is equal to minus of x plus y. Okay, so in the case, now I can from the third equation. I'll get 2z plus lambda 1 minus 2. Okay, and then I have lambda 2 which is minus 2 times x is equal to 0, or x plus y minus z plus 1 is equal to 0. So this will be the same equation here. And then I can also have again, the constraint equation, which is that I have x minus x plus 1 plus z, or z minus x. I have the equation minus x plus 5 equal to 0. And then I also have the equation which is x plus 5 plus z minus 1 equal to 0. Just x plus 5. Oh, at that I don't. Okay, let me wipe it. Okay, so I have z minus x5 plus 5 is equal to 0, and then x plus 5 and then if I look at these two equations, okay, then what I get is the following. I have to have x is equal to minus 1, so and z is equal to 1. Okay, and if I look at a third equation, modulus x equal to modulus y equal to 2. Okay, so these are the conditions under which we will this all the 5 equations, right? So which would mean that I must get the following, that is I must take x equal to 2, y equal to minus 2, z equal to 1 is one particular point, and the second point that I can think of is x is equal to minus 2, y is equal to 2, and again z is equal to 1. So if I take these are the two solutions that I have. This is point 1 and this is point 2, which are closest to the origin. Okay, and so I'm being able to do this by using the Lagrange multipliers. What I did was first determine the Lagrange multipliers and then use this in the third equation for dz, and then I also use the constraints, and using these two equations I can get the x, y, z value. So usually this is to do in anything else. So this is just an example of Lagrange multipliers I wanted to give you. So you know, trying to map this. What I now want to do is I want to try to proper calculate. Okay, calculus is an extremely important thing for both physics and chemistry, because we use calculus of variations either knowingly or unknowingly in many cases. So to understand what is calculus of variation, understand what a function is. Okay, a functional is one that returns a number given a function y of x. I am just talking about this. It's much easier to make all these things clear with one dimension. Number given a function of x and an interval a comma b. So this is very different from a functional. Examples of a functional are, for example, I can put is a equal to integral a to b yx Okay, so this is going to give me the area between the points x equal to a and x equal to b, the area under the curve. Okay, so that is one example. Okay, and for example, an integral is a function as given a function, it returns an number. Whereas in the case of function, for every a point that you give, then it gives another point. That is, given a number, it returns a number. You don't have to give a function. This is the difference between functions and functions. For example, function, what it does is give a number, the function returns a number. For example, I can have f of x equal to x. You give x equal to 2, then f of x is equal to 4. So it gives a number back. Okay. Whereas a function like integral f of x dx a to b is going to give me, b cubed minus a cubed by 3, which is actually a number. So given an entire function in the interval, it gives a number. Whereas a function returns a number for every number that I give. Okay. So now, what we're interested in is, we want to know the function which minimizes the function. Let me spend some time on it. So examples are the following. Given 2 points A and B, on a plane. Okay, so I'm given 2 points A and B. Okay, I want to the curve joining A and B. Which has minimum length. Okay, so it can be one function can be y1, another function can be y2, and a third one can be y3, and so forth. So I want to find out from amongst y1, y2, y3, infinite number of functions that can be drawn between A and B. This is the function that gives the distance between A and B, which is minimum. And what is the distance between A and B given time? Okay, the distance between A and B, or the length of curve between A and B along a curve y of x is given by integral a to b, let me call it a to b, square root of 1 plus dy by dx the whole square times dx. Why is this? Because you know that the length element ds is equal to dx square plus dy square. So this is what we know from Pythagoras theorem. Okay, so if dx square is equal to dx plus dy square, then dl is equal to square root of dx squared plus dy squared, or that's equal to square root of 1 plus dy squared by dx squared into dx, or that's equal to root of 1 plus y prime squared dx. So I want to find out, this is a functional I, We want to minimize I. We want to find the curve y of x, which minimizes I. So this is one such example, okay, that I can give you, which is a simple example. And any similar examples. Well, let me look at the problem of what's called geodesics. Okay, you can also have constraints for this problem. For example, let me take a sphere. Is a sphere or a surface, okay, some sphere or surface, which is not a plane. So I want to find out the curve between A and B, that the curve between A and B lying on the surface and having a shortest distance. So the which means that it must be subject to a constraint that the integral I equal to integral U to B ds, which is the variable on that. This should be minimum subject to the constraint that along the curve C, subject to the constraint that C lies on the surface S. That means I have C, which is given by using x of t times I plus y of t times j plus z of t times k, should also satisfy the condition that say f of x comma y comma z is equal to constant. So this is the constraint because this gives me a surface and this is the curve, and I want to find out the length along the curve, which is satisfying this constraint and give me a minimum distance. Okay, so this is a constraint problem, which again you can solve using the Lagrange multiplier. But before that, I'll tell you what you will actually do to get to this state. Okay, and one of the most interesting and important problems that was ever posed is what's called the Brachistochrone problem. If you Google for Brachistochrone problem, you will come across its solution as well as the statement of the problem. This was the first problem in capital abbreviation that was actually posed and solved, as far as I can tell you. And the problem is the following: that is a frictionless bead on a string tied between 2 points A and B. I will have a figure for you. By A and B. Okay. And the string is lying in the plane. Okay, so what I have is a plane here. I have a point A here, and I have a point B here. Okay, B is below A. So now I will draw a string. Okay, and I have a bead. And the bead on the string, comma, point A will travel down to B. The question is, what is the shape of the string? for which the time taken to move from A to B is minimum. I want to have the fastest path by which the bead can travel down from A down to B. Okay, so it is called the Brachistochrone problem. Chrone actually means time. Okay, so this particular problem, it appears like the straight line. I'll just tell you the solution without trying into it. It's not the straight line joining A. In fact, it's one of the slower paths. Okay, for the straight line joining A and B, but is a cyclone going from A to B. Cyclone is a very interesting curve. You know, cyclone is what you take a circle or a wheel, and on this wheel you put a this thing patch somewhere there, and then roll this wheel down. Okay, so when you roll this wheel down, what happens is that it starts going up. The point will be going up as you keep rolling the wheel. Okay, it goes there, and then it goes up, and then it comes on the other side, and then it again comes down. Okay, so this curve that goes like this is the cycloid. Okay, and the solution for this is the cycloid. I'm not trying to solve the problem. Solution of the problem is also on the internet if you want to find out. It's quite an interesting solution, but it's a cumbersome solution. Okay, so I will not. Now, how I can solve this problem? Okay, so I want to minimize a function. First, get minimum function, minimizing function. That's true. Get the minimizing function. How to do that? It's important because supposing you look at physics, okay, physics is the Newton's laws of motion are actually formulated in terms of the least action principle. Okay, so what we have in physics, okay, the path taken by a particle from A to B is given by the path that minimizes the action. Let me apply action. Action is, so if I'm starting at a point at time t1 and then going to time t2, action is done by L, T, R, R dot dt. L is the Lagrangian. I have written the Lagrangian for a single particle in the absence of any electromagnetic fields. So that's why I have it in this form. L equal to T minus V. Okay, or equal to mv squared by 2 minus V of R. Okay, so that's the Lagrangian. So if you want to find out what is the path that is taken under the influence of V of R, for going from position from R1 T1 to R1 R2 at T2. So where I want to know solution is R of T, I want to know R of T between times T1 and T2, then I have to minimize action. Okay, and this is the one that gives us to all molecular dynamics equations and all. Okay, and in quantum mechanics, you keep doing another thing. We want to minimize energy in quantum mechanics. Actually, it is not strictly minimizing, it is making it stationary, which means that the first derivative of the energy function is always zero. So that is what we'll be doing. We want to minimize the energy from the ground state. So the energy function is done by E equal to integral psi star h psi d tau. So I want to minimize this subject to normalization condition integral psi star psi d tau equal to 1. So this is the constraint, and this is the function that we are going to minimize subject to this constraint. So this is another problem that you almost always encounter in all of chemistry. You are always dealing with obtaining energy eigenvalues of various Hamiltonians. Okay, so these are the two very, very important problems in chemistry and physics that involves minimizing functions. Now let us see how we can go about minimizing a simple function. So the functions that I'm is the following. Okay, so we want the function y of x, which minimizes the function y for the integral of, let me call it what f of x comma y of x comma y prime of x dx. So in the case of Lagrangian is basically a function of time, r of t, and r dot of t, which is differential of r with respect to time. Like I always said that whenever you are differentiating with respect to time, you put a dot on top of the variable to show that it is actually r dot is equal to dr by dt. But whenever you have a function of x, and phi prime is y by dt. So usually the notation used by specific. So now I want to minimize this. Okay, so I want to find y of x, which minimizes uh, I. Okay, so this is what my interest is. My interest is in finding the function. Okay, so I will have to think of a way of doing it. Assume the following. Assume that y of x, and you also have to specify the boundary that y of x is a function which actually minimizes I. What it means is the following. That is, so I have my y of x. So this is x1 by 1 and x2 by 2. So I have a function which is x1, y1, x2, y2. Okay, so this is y, this is x, and this is a function which minimizes right. Okay, so what it means is that now if I take any function y bar of x equal to y of x plus eta of x. Okay, where eta of x is something that has got eta of x satisfies the following boundary condition. Eta of x satisfies eta x1, eta x3. So I take this function and then I put, say, give an example of eta x, eta 1x. Okay, so any arbitrary function eta of x I add to this y of x, at y bar of x will always give me y bar of x will give integral f x y bar prime dx is always greater than I. Okay, which is given because y of x is the one that is minimizing this. So it is true for any arbitrary eta x. So if I want to look at just slight variations around y of x, then what I have is the following. That is, I can take small variation of the function the function can be written as y of x plus epsilon eta of x. Eta of x is arbitrary and satisfies homogeneous boundary condition at x1 and x2. Because you are adding it to x, y of x already satisfies the boundary condition. So if y of x plus epsilon eta x also should satisfy the boundary condition, eta x must be having a homogeneous boundary conditions at x1 and x2. That is, eta x must be vanishing at x1 and vanishing at x2. So if it vanishes, then if you add any function to y of x, you add any function eta 1x which has this boundary condition, then you will see that that is going to also satisfy the same boundary condition. It is giving you a different function. So what this means that now I can think of the integral as the following. The integral is x comma y plus epsilon e prime comma y prime plus epsilon theta prime. Okay, and this I can find along the prime. Right? If it is that, it's just like expanding f of x comma y comma z, except that instead of that you have y. So this is f of x comma y prime plus del f by del y epsilon eta x plus del f by del y prime epsilon eta prime. Okay, so this is just what we were expanding f x was in around because x we are not changing anything, so that is why del f by dx done. Okay, that's simply because not changing the value. Okay, so now if I do this, then I can say that I plus di is equal to uh, uh, integral f of x comma y plus comma y prime on theta prime of x dx. Okay, so I'm between the same points here. So I'm reading or exponent is not moving. Okay, point A and B are point exponent. So from now on, I'll just write instead of writing eta x and write it as eta. Is much easier for me. So if I do this one, A to B, f of x, y, y prime plus del f by del y, I'll write epsilon here, theta plus epsilon del f by del y prime, theta prime times dx. Okay, so if I were to take di is equal to epsilon times integral f. These are all partial. You have to be completely theta dx plus integral del f by del y prime theta prime dx. Okay, so I can look at di by d epsilon is given by limit epsilon 0 of the tablet quantity, so di by epsilon. Well, it's not moving. So let me, okay, di by epsilon is equal to integral del f by del theta dx plus integral del f by del y prime theta prime dx. Okay, in part D. Okay, and limit epsilon tending to 0 will give me di by d epsilon. That is equal to integral del f by del y theta dx plus integral a to b del f by del y prime theta prime dx. Okay, so I have almost got my algebra as if I'm trying to minimize di as if I is a function of epsilon. So this is minimizing I as a function of epsilon by using an arbitrary function eta of x and multiplying that by epsilon and adding it to y. So I'm almost dealing with it as if it's the calculus of maxima and minima becomes calculus of variation. Okay, so which means that I is an extreme. If di by d epsilon equals 0. Okay, right? Because that's what we always know from already maximum minimum, and that here the dx should be equal to 0. And so what we have done is we have expressed it as though it's a function of a single variable epsilon, so that the integral changes every time we change epsilon, and eta is some arbitrary function, homogeneous quantity point in P, and it is added to y. So if this is the case, then what we should do is the function y of x should minimize, should be such that for any arbitrary integral a to b del f by del y eta dx plus integral a to b del f by del y eta prime dx is equal to 0. Now what I am going to do is I want to integrate the second one by parts. Okay. This we can integrate by parts. We get integral to b del f by del y eta dx. So what I'm going to do is I will integrate eta prime and differentiate del f by del y prime. Okay. So that's how I'm going to do it. So this will be plus del f by del y prime into eta, okay, between a and b minus integral a to b. I will differentiate this with respect to pH. Del f by del y prime times eta dx is equal to 0. Okay, so what you notice is that this quantity is going to be 0 since eta a equal to eta b equal to 0, because that's the way I define eta, right? So because of this, I can write down the condition as a to b del f by del y minus d by d del f by del y prime times eta dx is equal to 0 for any arbitrary function eta x subject to the above boundary condition. Okay, now I can use what's called the fundamental lemma of calculus of variance. It's a very simple lemma. What does this fundamental lemma of the calculus of variance tell you? That any integral a to b some fx eta x dx equal to 0 for arbitrary x, then fx is identical. So that is quite simple. Now assume, how do you prove it? So if fx is not equal to 0 on point x, choose eta x such that eta x at that point, okay, such that fx eta x is greater than 0. So if fx is like -1, choose eta x is equal to -1, so that fx eta x is equal to greater than 0. Similarly, if fx is +1, at that point you choose eta x is equal to +1, so that fx eta x is equal to +1. And because eta x is arbitrary, you can choose any value. And at all the other points where it is 0, it does not matter what you choose eta x as. So if this happens, then the integrand is not identically 0. And if the integrand is not identically 0 and also positive, is of the same sign, because you have taken fx eta x greater than 0 whenever fx is not equal to 0, and is also positive, which means the integral is non-zero. So if the integral should be 0, it means that fx must be. So hence, for the integral to be 0, for arbitrary eta, f of x must be identical. Okay, so that is you look at the, so what was the integral that I had? Okay, I had integral del f by delta dx del f by del y times eta was integral. So this implies that del f by del y minus d by dx del f by del y prime is equal to 0. If the first variation in I must be 0. Because that's what you say, the first variation is 0, and we're now getting about the second variation. Second variation should be positive if it has to be the minimum, and the second variation should be a negative if it has to be a maximum. And that is simply because if you do a Taylor series expansion, you see that a second higher term is the second derivative. And since we are adding it to 0, if that is positive, then you will have a minimum. Okay, so we can simplify this. So this is what is known as the Euler. Okay, so Euler Lagrange equation has to be satisfied. So the differential equation. You get this? So you see d by dx delta f delta y prime actually over total. Okay, so how do you get it? You get the total derivative as del f by del y prime plus del by del y del f by del y prime dy by dx plus del by del y prime del f by del y prime dy prime by dx. Okay, and what is dy prime by dx? So that's equal to this whole thing as f of x comma y prime. So where the subscript x and y prime that we are differentiating with respect to x and partially differentiating f with respect to x and y prime. And the second one is going to be f of y prime dy by dx plus f of y prime d squared y by dx. Okay, so the Euler So just change the sign. Let me start. So I can also transform f y prime d squared plus f y by prime dy by plus uh, f of x y prime minus f of y is equal to 0. So this is the equation, differential equation we have solved. So this is the Euler-Lagrange difference. Which has to be, which is a second order differential equation, and needs to be solved to obtain the minimizing function by f. So if we want to find out the function y of x, it is going to be minimizing the integral f of x comma y prime dx, then it must satisfy this difference. Okay, and this is a you can have the Euler-Lagrange differential equation. You want to be a function of x1, x, y, and if it's a rather it will be a function of f of z1, y1 rather. So actually you'll have a time you'll have a simple function, you'll have the Lagrangian will be a function of time, and then x of t, y of t, z of t is r of t, and x dot t, y dot t, z dot t is r dot of t. So for a single particle, what you have is Lagrangian is just t comma r comma. So this is the one that you have to minimize integral t comma r dot dt between time t1 and t2 to actually get the path the particle follows, namely r of t, given the potential v of r. Okay, so it is actually it will be a three-dimensional problem that you have to solve. But supposing you have got 100 particles, okay, so Lagrangian is now a variable which was 301, 601 variables, right? So because R will be 300 variables, x, y, z of each particle, R dot will be x dot t, y dot t, z dot t of 300 variables, and time itself is another variable. So you have 301 variables, and you have to solve it. And that is done on a computer using the molecular dynamic simulations. But you'll have to set up these are the equations. How you solve one by one, or when you solve all of them together is okay. So now I just try to give you a simple thing for this. You see, because whenever you use the Euler-Lagrange equation, that actually gives rise to the Newton's law of motion. Okay. So to understand this, let us follow. Let us consider harmonic oscillation. So what is the that is equal to half of dot square. Let me see whether it will write it. One second. My computer is freezing a little bit. So let me try. I have it's writing in the other part of the plate. So I have t is equal to half of mx squared and b is equal to half of kx squared. K is the force constant. So, okay. So it's not opening, it's not writing. So let me open another page. Okay. Maybe it will. Yeah. No, it's better. Okay. So I have t is equal to half of mx dot squared. X dot is a velocity. X dot is equal to dx by dt. And v is equal to half of kx squared. And that is the potential. So basically, you have a spring and you have an equilibrium distance r naught, and x is equal to r minus r naught, which is when you plug it. Okay, and the kinetic energy is what half of it, and potential energy kx squared. So m is equal to e minus p is equal to half of mx dot squared minus r minus kx squared. And I have to minimize this quantity of mx dot squared minus kx dot squared by 2 dt in going from T1 to T2. Okay, so let me get the first of T because I'm going to start. There's no need to get exact. So I have L of this thing is given. So the order Lagrange equation should be action. So the function of T, which minimizes the action, is given by let me write understand the following. I have to get del L by del x. Sorry, this is not x dot square. Okay, del L by del x is equal to minus k. Okay, and so this is the equivalent of y. Okay, and then I have ln by del x dot is equal to mx dot or del squared L by del x dot del x dot del x dot. Del squared x dot is equal to m. Okay, so that is one thing that I will get, and then I have all the others are all zero. Ln by del squared L del x del x is equal to zero, right? And then this will be this will be zero because once you differentiate you get mx dot, and that if you differentiate is going to be zero. And similarly, so this is f of x prime. This is the equivalent of f of x prime, and this is the equivalent of f of y prime. And then I also have f of y prime comma y. So what is the equivalent of f of y prime? I have del by del x dot and del by del y, and that's equal to del by del x. That's equal to 0, and this is the equivalent of f of this I've already show it again. So I have all the coordinates that I need to know. So I will get the first one, which is del squared L by del x squared, that is f of y prime d squared y by dx squared will now become m d squared x by dt squared. Okay, and the second one, f y prime y is equal to 0, and f so I tell you f of x y prime is equal to 0, f of or L of del squared L by del r dot L, del r x dot del this is f of y prime. So that I have already taken. So what I have the non-zero terms are and then f of y, which is not zero. So what I have is the equation will now be f d squared x by dt squared plus kx is equal to 0 because the fy comes with a minus sign. Sorry, I lost the other one. Is in the other notes. So what is this? So this is going to give you mx double dot is equal to minus kx. And what is mx double dot? This is the force. Okay. And what is this? This is the force due to spring. Okay. So this is nothing but the Hooke's law. So you see that I was able to get the Hooke's law by using the Heisenberg-Lagrange equation and the Lagrangian for the problem, which is the harmonic oscillator problem. In fact, more basic than Newton's equations is actually the Euler-Lagrange equations and the action principle. And the action principle is the one that is almost universally used. For example, even in the case of optics, you have the Fermat's principle. Okay, Fermat's principle just says that light is the fastest path to 2.3. Okay, So the fastest path also that is the Fermat's principle, and you see that that is going to tell you how the refraction and the refraction takes place at surfaces. So and there's also like the Lagrange equation. Okay, is like the least action. All these things are very similar. So now what I'm going to do is I just a general almost universal for solving the exercising problem, the uh, so the Rayleigh principle, what you are going to, that is approximate the solution of y of x by a series of by as an after process. So what you are going to do is y of x is equal to p1 of x plus p2 of x, etc. Let us take n. Okay. So if I am looking at yx h yx dx, okay, and uh, I'm going to if I don't so this uh, divided by integral yx dx, okay. So this is x to h. So I want to minimize e. Okay, so now I substitute for e. So when I substitute for e, what is e is equal to sigma over I equal to 1 sigma over j equal to 1 to n IISC. Remember that I'm using everything as real. Okay, integral pi h pj dx divided by sigma over I sigma over j. Okay, integral CICJ. Sorry, CICJ integral a star p rather pi pj dx. I'm just using everything as real and single value. Okay, so now if we can evaluate integral pi pj dx and call it a okay, then what happens is we can write our E as, and we also have integral pi pj dx is equal to delta ij. So I have E times E is equal to sigma over I sigma over j equal to 1 to n pi cj hij divided by sigma over I ci square. Okay, so this is what I will get, and I can then write so E ci square E into sigma over I ci square is equal to sigma over I j equal to 1 to n PICJ HIJ. Okay, to minimize this, now since varying the function of x is equivalent to varying the function C1, C2, etc. Almost like what we did with only one particular function of x, instead of that, we are now having a series of functions C1 and C2. So, since E has to be minimized. In fact, extremized. What we have is we have to put E times sigma over I. So if I differentiate CI, okay, so then what I'm getting E times, so if I differentiate CK, you see, 2ECK is equal to sigma over I is equal to 1 to, or rather, is equal to 1. CK, CKCJ, HKJ. Okay, so I can cancel out CK, and what I'll get is this will be actually because I will have CK coming. No, need not be matter. So I have E is equal to sigma over ECK is equal to sigma over J is equal to 1 to TJ HKJ by. I have, for some reason, I have missed a fact. Okay, so according to that, I can write down sigma over J is equal to, let me write it. Is equal to ECK for K equal to 1 to X. So what you have is you have a set of functions which are eigenvalue, eigenvalue. So this is actually a matrix eigenvalue problem. We can obtain E, M, and the function y of L, okay, as the solutions for the extremum problem. So you see how suddenly we have converted this extremum problem using a basis into a problem which involves a matrix eigenvalue. Okay, and you also find one more thing, that is, since we are looking for a minimum, we can compute the lowest eigenvalue E0 for various values for different number of basis functions. So as long as you are just adding new basis functions, that is, first I will take P1, and then I'll take P1 comma P, and then I'll take P1 comma P2 comma P3, etc. etc. So this is n equal to 1, n equal to 2, n equal to 3. So in all these cases, what I'm doing is I'm adding an extra function. Okay. So as long as that is the case, then what we will also have is E1 greater than or equal to E01 greater than or equal to 2 greater than or equal to 3, etc. This because it is almost like using coordinates, right? So you know that if you are having a multi-value function and you want to find out its minimum, so the minimum in one dimension you can get is always going to be greater than or equal to the minimum in 2 dimensions, greater than or equal to the minimum in 3 dimensions, and so forth. For example, let me take the following, okay? Let me take a parabola. Okay, so If I'm trying to look at it in one dimension, then I'm only looking at one of the sections. And in this section, okay, this paraboloid that I have is going to intersect this one, and you get a parabola which corresponds to this, right? Because this is actually a paraboloid, a three-dimensional thing. So you have actually got a cone. You cut the cone, and then you get one plane. Okay. So now, if you go to higher dimensions and keep cutting it, then you will see that the minima will approach this one. In 2 dimensions. If I cut, varying, pushing it up and down, like for example, I'll keep taking the cuts in different dimensions. Okay, so this will be the minimum, this will be the minimum, and so on and so forth. So if I keep trying out the minimum in different dimensions, then I'm going to come to the absolute minimum, right? So this is what it says. So as you increase the number of basis functions, the minima becomes lower and lower and lower. But this is true only when you are adding a function to the earlier basis. If you are completely changing the basis, it's not. Okay. Supposing first time you take P1, second time you take P1, P2, and the third time you take P2, P3, P4, and take P1, then this relationship will not hold. Okay. This relationship will hold only when you are adding one more function, not when you are having more functions, but different functions. That will not work. Okay. So in this fashion, we can get the problem. This is how you take, this is the way you get like local or any other one particle thing, three particle thing, like, or any other one. And obtain the extreme value. So I have given you some small flavor of the calculus of variations and how it is useful in molecular dynamics and quantum mechanics. And I think I will stop my course here. This will be my last class. Because next week is going to be the Christmas week and the holiday week where I am things. So I will stop this and I enjoyed giving this course, but I'm really sorry that there were times when the internet connections were not very good and you could not hear what I was speaking clearly. But I hope the references and tutors will be able to see you through this difficult time. And we will have the exam on 5th of Jan, as we had said earlier. And I will take you at this point and wish you all the best for your exams. Thank you very much.
Thank you, sir.
Okay. So,
Thank you, sir.
okay, all the best and all the very best for the new year. Bye.
Thank you, sir.
Okay, bye.
Bye, sir.
Bye, sir.
Bye.